Hello, everybody. Today we are doing a lesson about number properties. Number properties refer to the properties of integer numbers. Let's begin. Integers are numbers that don't have decimal parts. Here you have some examples. Negative integers such as -5, -4, -1, etc. You have 0, is also an integer, and numbers 1, 2, 3, 4, etc. Also called natural numbers, right? In the GMAT, sometimes they talk about non-zero integers. That means a number with a sign. That means an integer that can be positive or negative. It is very important that you be clear on what numbers you can use in a given problem. For example, if the question mentions if x is an integer, automatically think about this question. What are they, the test makers, not restricting you when they tell you that x is an integer? For example, in this case, they are not restricting the sign, right? They are not restricting 0, etc. If they tell you if x is a positive number, what are they not restricting? Well, they are not restricting fractions, for example, or decimals, right? It could be fractions, decimals, integers, etc. So it's very important that when there is a mention of the type of number a variable is, you think about the restrictions. In that case, you will be forced to think about all the possible cases, all right? And so not to miss a special case that could change the answer to your question. The first property of integers is even and odd numbers. Even and odd numbers are numbers that end respectively, okay? Numbers ending in 0, 2, 4, 6, 8. And what about odd numbers? Odd are numbers ending in 1, 3, 5, 7, and 9. These are odd numbers. There are certain rules that can predict the result of an addition or a subtraction or the multiplication of even and odd numbers. For example, if they are the same, even or odd, the result will be as an even sum or an even difference. But if they are different, one even and the other term odd, no matter in which order, the result will always be an odd sum or difference. What about the product or multiplication? In a multiplication, the two factors need to be odd if you want an odd result. But for a product to be even, all you need is just one factor even. So it could be even odd or odd times even or two evens. You will get an even product. Okay? What happens when you have powers? That is to say, a number like this, right? X up to n. What happens when the base of this power is even? So if the base is even, then the result is an even number. But if the base is an odd number, the power of an odd number will always be odd. What happens with exponents? Here, if the exponent is an even number, then the power of an integer will always be positive or 0, right? But on the other hand, if the exponent is odd, the power keeps the same sign as the base. So keep in mind these rules. Example, right? If you have -2 up to, that will always be positive. this is a positive value. And if you have 0 up to 2, that will be 0, right? What happens if you have -2 up to 3? Well, since 3 is an odd exponent, the result will be -8, a negative number. But if you have, for example, 2 up to 5, well, 2 is positive, so this power will also be positive, okay? Same as the sign of 2. Let's see how can we solve one problem, right? Using these properties. If 3x plus 1 times y squared plus 6 is odd, is x plus y even? We know that this product of these two factors equals an odd number. Well then, if you have two factors that multiply give you an odd product, it's because each of them is an odd factor. So we analyze each factor separately. 3x plus 1 is odd. What does this mean? It means that we have a sum. Here we have an odd value, so the other should be an even value, because even plus odd gives you odd. And if 3x is even, then this product, 3 multiplied by x, is even only if one of them is even. Since 3 is not even, it follows that x must be the even one, because 3 is odd. So odd times an even gives you even. From this, we conclude x must be an even number. What about y? Y squared plus 6 gives an odd factor. So, since 6 is already an even number, you can sum an even plus an odd to get an odd result. So, that means y squared should be an odd power, but this could only mean that y is an odd base, because powers keep the same odd or even value as the base. Now, from these two, I can conclude that the sum of x plus y, which is an even plus an odd, will be an odd value. So the answer to the question is no. Okay? With these properties, you can do these examples, these exercises, without having to plug in or insert values for the variables. Okay? So let's move on to the next concept. Let's talk about now prime numbers. Prime numbers are integers that only have two different factors, 1 and itself. Example, numbers 2, 3, 5, 7, 11, 13, etc. All these numbers have something in common. They can only be divided by 1 and by themselves, not by any other factor. For the GMAT, prime numbers are very important because prime numbers are actually like the building blocks of all other integers. If an integer is not prime, it follows that an integer should be a product of prime numbers. Example, number 4 is the product of 2 times 2, which means 2 squared. Number, for example, 12 equals 4 times 3, but here you have 4 is the square of 2 multiplied by 3. So you see any non-prime number, also called composite, can be factored or can be expressed as the product of prime factors if the number is not prime. Okay, so the prime factorization, finding this product of prime factors for any given integer, you can do it old-fashioned, like old school, but this is time-consuming. Okay, If you can do it in blocks of numbers, you can do it faster because you write less. For example, 72 is the product of 8 times 9, according to a multiplication table. So 8 can be expressed as 2 cubed and 9 as 3 squared. So that's the factorization of 72. You can practice, factoring bigger numbers using this approach. Example, if we factor 144,000, I can, split this into 144 times 100. But 144 is the square of 12, and this is the square of 10. Using the properties of powers and exponents, can say this means 3 squared times 4 squared times 2 squared times 5 squared. All we need to do is express now as a power of 2, which is 24 times 2 squared. This will be 6. So eventually, 144,000 can be expressed as 2 up to 6 times 3 squared times 5 squared. And that's it. That's the whole factorization of 144,000. Okay? Would be a good idea for you people to remember all the primes less than 100, because these primes are often seen in problems about integers. Let's discuss the concept now of factors and multiples. Okay, factors and multiples is a concept that only applies to integers. What does a factor of an integer mean? A factor of an integer is a number by which an integer can be divided evenly. Example, if we take number 12, for example, the factors of 12 would be numbers such as 12, 6, 4, 3, 2, and 1. You can divide 12 by any of these other integers and get an integer as a result, an integer quotient, right? On the other hand, a multiple of 12 would be a number that contains 12 an even number of times, okay? So that is, for example, 12, 24, 36, 48. If you divide all these numbers by 12, you also get an integer. So these two concepts are actually reciprocal. For example, you can say 5 is a factor of 15, or 5 is a divisor of 15. And this means that 15 is a multiple of 5, or 15 is divisible by 5. These two expressions are like inverse. And they are used as synonyms actually in problems. How do we represent the relationship between a factor and a multiple? Okay, well, the four expressions here can be represented in two main forms. The first one is to say if x is a multiple of y or x is divisible by y, which means also the same as y is a factor of x or y is a divisor of x. Then it follows that x over y should be an integer. That means x divided by y should be an integer, or x could be expressed as the product of y multiplied by another integer. In most GMAT problems, they usually work with the positive factors of an integer or the positive multiples. They even tell you the positive factors or positive divisors. But remember, 0 is a special number which is at the same time a multiple of all integers, right? You could represent 0 in this way. 0 divided by any integer y actually gives you a 0 as a result, which is an integer, right? And on the other hand, 1 is a universal factor. You can also express like this. Any number any integer x can be expressed as the product of 1 multiplied by the same integer. So these two facts are very important, okay, in this theory. Let's now consider one example on how to use this form of representing, right, the criteria of x being a multiple of y. If x and y are positive integers, is x a multiple of y? Let's first reformulate our question using the equivalent criterion that x divided by y should be an integer. This will be our question, okay? And now, in statement 1, we have an equation connecting two variables, y and x. What's our purpose after we reformulated the question? Well, we're trying to see what form this expression x over y has when we try to isolate the expression from the statements. For example, here, if I divide by y, I would get that x over y would be y plus 3. All right? So I can tell the division of x and y gives you this expression. Since y is defined as a positive integer, then it follows that the whole thing, this sum, should be an integer because I'm adding two integers, y and 3. Since everything is an integer, the quotient x over y, this means that x is a multiple of y. So we have an affirmative answer to the question, and this is sufficient. Okay, so let's now check statement 2. Statement 2 says that x times x plus 2 is a multiple of y. Well, what does it mean? That x times x plus 2, when divided by y, should yield an integer. But the purpose we have is to check what this quotient looks like. So I try and isolate this quotient, okay? Let's do it. X over y would be an integer divided by x plus 2. So now let's analyze this expression to check whether is always an integer or not. But you know x is an integer. So an integer plus 2 gives you another integer. So this clearly can be expressed as an integer, a certain integer 1, divided by a certain integer 2. We know that the quotient of two integers is not always, right? Not always integer. Sometimes it might be, sometimes it might not. So this means we don't have a definite answer for the question, and that is not sufficient. So the answer choice would be A. Know that you don't have a clue as to what the real values of x and y are. We can never know what x and y are, but we know for certain that x must be the multiple of y in the first state, okay? Let's check another concept. The number of factors. What is the number of factors? Well, here we're talking about a number, right? Like, for example, 36. Imagine 36. If you factor 36 and express it as a product of primes, you would have 4 times 9. So this would be the factorization of 36. Now, if we want to count how many factors does 36 have, then we do the following. We take the exponents, add 2, add 1 plus 2, 2 plus 1, and then we get 3 and 3. We multiply this and get 9 factors. Okay, one more time. You factor 36, you check out the exponents of the prime factors, add 1 to each of the exponents, and then multiply the exponents. So you get the total number of factors of 36. Let's check. Here are the 9 factors. 1, 2, 3, 4, 6, 9, 12, 18, 36. You know, the easiest way to find all the factors of a number, especially if it is a short number, is try to make a little table. Okay? Here, we want to identify pairs of factors that multiply by each other gives you a 36. Example, 36 times 1, right? Or 18 times 2, or 12 times 3, or 9 times 4, or 6 times 6. So you can identify all the factors are here. The first 5 factors and the second 4. Totally 9 factors. These factors only include 2 prime factors, but the others are not prime numbers. Okay, so in general, we can say, if we know that a certain integer can be factored as the product of certain prime numbers, and we identify the exponent of each of the prime factors of the number, then what you need to do is identify the exponents, add 1 to each exponent, and then multiply the 3 results. That product will give you the number of factors of that integer, okay? Another conclusion from this theory is that consecutive integers, that means numbers that have a difference of 1, they don't share any factors other than 1. Examples, for example, 35 and 36, no common factors, right? The same goes for x and x plus 1, no common factors. And if they tell you, for example, that x is a multiple of 9 times another integer, then it follows that x plus 1 cannot be a multiple of 9, okay? Because they cannot share any factors. All right, so with this concept, we can estimate the number of total factors that any integer has, especially when they are not primed, right? If they are composite integers, you can use this formula to calculate the number of factors. Let's talk about now a certain problem that involves integers, especially when they tell you that the power of an integer, let it be the square or the cube of a certain integer, is divisible by some other integer. It is important that the exponents in the prime factorization of that divisor have to be multiples of the exponent here, right? Let's see an example to better understand this. If x is a positive integer such that x squared is a multiple of 56, what is the least possible value of x? Well, we can express this way. X squared equals 56 multiplied by some integer. But 56, when we factor it, is 2 cubed times 7. 8 times 7, right? Multiplied by a certain integer. Well, from this, you know that this side of the equation should be the square of x. But how could it be the square if these exponents are not divisible by 2. For a number to have a square root that is also an integer, the exponent should be divisible by 2, right? Example, 6 up to 4, I know that when I take the square root of this, I will get an integer. How so? Because you apply the property 6 up to 4 divided by 2, the index of the radical here, right? Here is like 2. So 6 up to 4 divided by 2 is 6 up to 2, and this is an integer, right? So that means that if a power has an exponent that is multiple of 2, then it follows that the number has an integer square root. In this case, neither 2 nor 7 has an even exponent. So this means that this integer should complete the missing factors. Yes, we need some more factors here so that the whole thing could be a square. So what are then the minimum factors we need to complete so that x squared has its minimum value? If we multiply 56 by 2 times 7, we are adding one more, right, factor here, and we're adding one more factor here. So when we do the multiplication, you will have 2 up to 4 times 7 up to 2. In this way, now you can find the minimum value of x. You just take the square root of the two sides of the equation, and you will get 2 squared times 2, 7. And this is 28. So this is the answer. This is the minimum value of x that has a square that is a multiple of 56. Let's try, with another number, such as 63 instead of 56. Okay, let's see another example. Let's say that we have x squared equals 63 times an integer. That is, the square of x is a multiple of 63. Okay, let's factor 63. This is 9 times 7, so 3 squared times 7 times an integer. Okay, now let's imagine what other factors we need to complete in this product so that this might be the square of x. Well, if we talk about the minimum value for x squared, right, then we should also minimize this factor, this integer. So at least we need just one more 7, because 3 squared times 7 gives us 3 squared times 7 squared. And now getting the minimum value of x just means to take the square root on both sides. So if you take the square root, you get 3 times 7, which is 21. Okay? We can do this also with the cube of an integer. Let's do it here. Let's try to solve the original problem, right, with 56, okay, and the cube of 50 of x. If they tell me that x cubed is a multiple of 56, then it follows that x cubed would be 2 cubed times 7 times an integer. All right? So, for this, expression to be the cube of x, well, we need that the exponents are actually divisible by 3. Well, here we have one exponent that already complies, but this exponent here doesn't. So what we need is that this integer can aggregate the exponents that we are missing. So for the minimum value of x cubed, I would use the minimum factor with additional numbers that can complete the exponents being multiples of 3. So if I multiply this by 7 squared, okay, this will become 2 cubed times 7 cubed. And so the minimum value of x would be achieved by taking the cube root on both sides. You take the cube root of 2 squared times 7, 2 cubed times 7 cubed, and you get 2 times 7, and that is 14. All right? So you can see this property is interesting because you can solve the minimum value possible for a certain variable, integer variable, whose power, let it be the square or the cube of that integer, is a multiple of a given divisor. Let's now visit the last concept of this lesson, which is the greatest common divisor, or GCD, and the least common multiple. Finding the greatest common divisor, the least common multiple for numbers that are small enough, you can do it, you know, like the high school method you were taught. Okay, example. If they tell me, okay, find the greatest common divisor of 2, 6, and I don't know, let's say 4, okay? The greatest common divisor, I just check by which common factor you can divide continuously all 3 numbers. I can divide by 2, I get a 1, I get a 3, I get a 2. I have no other divisor I can divide by except 1. So that would be it. This is the GCD. What about the least common multiple? I can do it also in that way, but this is different now. First, I divide by 2, all the times possible. Divide by 2, divide by 2, by 2. Can I divide by 2 again? Yes, this one. So I divide by 2, this remains the same. Divide by 2, get 1. I cannot divide by 2 anymore with an integer result. So now I start dividing by 3. Okay, this is just 1, 3 divided by 3 is 1, 1. Now I have all these factors here, is 2 squared times 3. And that is our LCM, the least common multiple. So the greatest common divisor is the common divisor among several numbers that is the biggest possible, the largest factor that can divide all the numbers evenly. And the least common multiple is the smallest multiple that contains all the numbers. But when the numbers are bigger, you can do this. You can use the prime factorization to find the GCD or the least common multiple much faster. Let's do this exercise with 180, 24, and 720. Now, you have the numbers already factored here as products of prime factors. So how do you find the GCD for numbers that are already factored? Well, the rule is very simple. Take all common primes common to all the numbers with the least exponent for each prime. So what are the common primes here? Are 2 and 3, right? 2 and 3. And 2 and 3 appear with the least exponents of 2 and 1 respectively. So I just copy those least exponents and I get the GCD or greatest common divisor, 12. What about the least common multiple? What's the procedure? Now I need to check all the prime factors participating in these numbers. 2, 3, 5. And then I copy the greatest possible exponent, 4, 2, and 1. So actually, this is just a copy of the third number, 720, right? Because in actuality, 720 is already a multiple of both 180 and 24. So that's why this common multiple is that very number. Okay, people.